In this lecture, we want to prove the formulation we introduced for the ratio of the angular velocities. We will prove the formulation for direct motion transmission, but it will also be valid for the case of indirect motion transmission. If we name the contact point as P, we can imagine there is a point P2 belonging to link 2, and there is also a point P3 belonging to link 3. Because of the contact, point P2 and P3 are coincident, meaning that they have the same position, but they have different velocities. Let's start with computing the velocities of P2 and P3. In order to find the velocity of P2, if I connect P2 to the rotation center of link 2, the velocity of P2 is perpendicular to this line. Velocity of P2. I call the endpoint of this vector S2. And the magnitude of the velocity of P2 is omega 2 times O2P. From there, omega 2 is the velocity of P2 over O2P. Similarly, for the velocity of P3, if I connect P3 to the rotation center of link 3, the velocity of P3 is perpendicular to this line. Velocity of P3. I call the endpoint of this vector S3. And the magnitude of the velocity of P3 is omega 3 times O3P. From there, omega 3 is velocity of P3 over O3P. Therefore, the ratio of omega 2 to omega 3 is something over something, which is velocity of P2 over O2P, and this one velocity of P3 over O3P. We should notice that in order to keep the links in contact, the normal components of the velocities of P2 and P3 must be identical. This is the velocity of P2. If I project it on the normal direction and name the intersection as S, then PS is the normal component of the velocity of P2. And this one is the velocity of P3. As we expected, its normal component is the same as that of P2. Let's assume this angle here is alpha 2. It has two sides, side 1, side 2. Side 1 is perpendicular to this line, and side 2 is perpendicular to this line. From basic geometry, we know that if the sides of an angle are perpendicular to the sides of another angle, those angles are equal. Therefore, this angle must also be alpha 2. Similarly, if we assume this angle is alpha 3, it has two sides, side 1, side 2. Side 1 is perpendicular to this line, and side 2 is perpendicular to this line. Therefore, this angle must also be alpha 3. We need to add two more lines. A line from the center of link 2 here, perpendicular to the line of transmission. Let's call the intersection as H2. Similarly, a line from the center of link 3 perpendicular to the line of transmission, and we call the intersection as H3. Let's focus on this triangle, the triangle SPS2. It has a right angle here and an alpha 2 angle here. Now let's think of this triangle, the triangle H2O2P. It has a right angle here and an alpha 2 angle here. What does that mean? From basic geometry, we know that whenever two angles of two triangles are identical, they are similar. Therefore, the triangle SPS2 is similar to the triangle H2O2P. Let's use the fact that their corresponding sides are proportional. In the triangle SPS2, opposite to the right angle, we have this side, which is velocity of P2. And opposite to the alpha 2 angle, we have this side, PS. Correspondingly, in the triangle H2O2P, opposite to the right angle, we have O2P. And opposite to the alpha 2 angle, we have this side, O2H2. The same story again happens here. The triangle SPS3 has a right angle here and an alpha 3 angle here, which is similar to the triangle H3O3P, which has a right angle here and an alpha 3 angle here. Let's write the ratio between sides. In the triangle SPS3, opposite to the right angle, we have this side, which is velocity of P3. And opposite to the alpha 3 angle, we have this side, PS. Correspondingly, in the triangle H3O3P, opposite to the right angle, we have O3P, and opposite to the alpha 3 angle, we have this side, O3H3. Now, let's go back to the ratio of the angular velocities. In place of this term, which is the same as this one, we can use this guy, PS over O2H2. And in place of this term, which is the same as this one, we can use this guy, PS over O3H3. Then, if we cancel PS with PS, we have O3H3 over O2H2. Now, due to the similarity of the triangles QO2H2 and QO3H3, we could say in this small triangle, opposite to the angle Q, we have O3H3, and opposite to the right angle, we have O3Q. In the big triangle, opposite to the angle Q, we have O2H2, and opposite to the right angle, we have O2Q. Therefore, instead of this term, which is the same as this one, we can use this guy, O3Q over O2Q. So the final formulation for the ratio of the angular velocities becomes omega 2 angular velocity of follower over omega 3 angular velocity of driver is equal to O3Q over O2Q. And we notice that point Q is the intersection of the line of transmission with the line of centers. For the rest of this section, we just practice how to apply this formulation to find the ratio of the angular velocities in different methods of motion transmission.